Hello and welcome to IEEE Soft Robotics Podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa Edwini, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks.
Hello and welcome to IEEE Soft Robotics Podcast. Hello, Fadel. Thanks so much for joining us in this podcast. Such an honor to have you.
Thank you very much for having me. It's great to be here.
Thank you. So I'd like to ask you first, how you'd like to define yourself for the audience who need the first time listening to you?
Sure, yeah, I'd be happy to describe myself on both a professional level and on a personal level. Professionally, I'm a researcher, I'm an academic, technologist, entrepreneur. I enjoy thinking about moonshot ideas and also investigating them to their core with scientific rigor, but then taking them out of the lab and deploying them in the real world for broad impact. Professionally, I spend most of my time as an associate professor at MIT, where I direct a research group called Signal Kinetics. My team investigates IoT, Internet of Things technologies that enable new capabilities that were not possible before. We do things like we could measure your heart rate from a distance through walls without requiring any sensor on your body, to enabling robots to see things that are invisible to the human eye. And I love the fact that we take our technologies from the lab and into the real world. But also professionally, I'm originally from Lebanon, and I've been in the US for the past 10 years now. So on a personal level, I identify as an Arab, as a Muslim, as a Lebanese, and as an American, all at the same time.
Wonderful. You're so passionate, and I deeply appreciate that. So I'm curious about your childhood. How was your childhood? Do you have any memories about your childhood, if you remember any?
A lot of memories. I mean, I grew up in Lebanon. I apparently, from a very young age, I really loved puzzles. During school, I remember being fascinated with science because it felt like magic. I loved science fiction, and science felt like it all was magic. And suddenly you're able to understand these things and they come to life. So I definitely remember a lot of that as part of my childhood. I apparently really liked to tinker with things and break our computer at home, just as a way to figure out what each different component did. So these are my scientific memories from my childhood while growing up.
Wonderful. Yeah. Do you remember what is the first system you built? What is the first MEP? I don't know, when you started undergrad student, and what kind of question you had in mind that you makes motivated to what you're doing right now?
I would say, like, I built a lot of systems. Of course, in undergrad, you start with more defined research projects that you're trying to build for a class. But then when I started having the agency to choose my own research direction, I was gravitated towards things that would sound like superpowers, like things that were not possible. What science, I think, is can take us. So the first research project where I had a lot of agency was actually during grad school, where I was researching whether you could use Wi-Fi to see through walls. And I would say that this was the first time that I really started with the project from its early conception all the way to building out a practical system.
And how you get these ideas? I don't know what kind of inspiration, because what you do is power, and like, for example, your PhD, how you get this? Because I think what's really hard is how to get the right question and the right problem. So how you manage to do that?
It's really part of a research environment and a research group that you are part of. So throughout my first year during grad school, I was in a lab which was directed by my advisor, Dina Katabi, and she had all of these sort of creative ideas. And we had a lot of technical knowledge in wireless, which was an area that attracted me personally. And then and I was involved with multiple different projects. I really wanted to build a lot of my skills and make sure that I first understand what is out there before I tried to go ahead and invent things that were not possible before. And my advisor always pushed us to think outside the box and think about what are the big problems and creative problems that we can address. And there was always the question of why. We had to justify why, like, why is this not working? Or why did you get this result? Can you explain this result? And I remember at some point we were in the lab and we were running experiments, putting actually antennas on robots. And what we wanted to do is to optimize wireless performance, to make throughput faster of Wi-Fi by moving sort of the robot to a better position. And we would move it to a better position. And every once in a while, the signal that we were getting between the transmitter and the receiver would sometimes, it would become very bad. And the throughput would go down. And we were like, we just moved the robot to a good place. And the robot is in its own room. So we knew in wireless that there's always this thing called noise. And then I realized that there's this this cleaning person who was walking back and forth behind the wall. And every time they would walk back and forth, the throughput was plummet. And inspired by my advisor, who would push us to always ask why, I started thinking why. And traditionally people knew this. People knew that this causes noise, this causes the channel to become bad. But then I started thinking, maybe this is something that is useful. Maybe there's information there. And maybe this noise itself is a way for us to understand this environment. And this is really what kicked off this whole project of, this is not noise. This is actually information in the signal that is coming back. And we can use it to see through walls and start tracking people and open up a lot of applications that we ourselves did not think were possible. And this came full circle to childhood dreams of superpowers and being able to push technology and science to do things that sound like magic.
That's very interesting. I don't know if that's something, how you managed to do that. Is it something intuitively, or because maybe sometimes people can like miss this kind of, it just maybe noise. How the technique with that? Because the student maybe sometimes has this moment then, and they don't figure out that would lead to something they never expected. Maybe counterintuitive sometimes.
I'm sure I've missed a lot of situations. I'm sure I've missed a lot of opportunities. The basic issue is that when something in science, you know, when we learn things in school, we really want to try to fit things into constructs that we've understood. But in science, the main thing when we're researchers, we want to question every result that we're getting, especially when we're doing experimental work. And also as engineers, we can take this questioning and try to tinker around with it so that we can play and start understanding where this source is coming from. And over the past years, now a lot of it with my students, most of our discoveries happen when something doesn't make sense. We want to try to run new experiments in order for us to like get good results, but then these results are not happening. And so when they are not happening, we start investigating why that is the case. And that really is what leads us to new discoveries. And then we start thinking about, okay, so this is very exciting, but how can we transform this into something that is useful and that can have applications in the world that can benefit society at large?
Wonderful. So I think from this start, you became more interested about sensing in general. I think that's something in the main. And when I'm speaking also about robotics or soft robotics, sensing is so challenging. How you can design a sensor that can sense the environment with less energy, and how, the accuracy would look like. So you can tell us more about the sensing itself, why it's so challenging. What are the questions you're trying to answer through your lab for designing sensor?
So my lab develops sensors. Actually, it's a sensor first lab. So we think about sensing as a fundamental primitive, and we try to think about how we could sense it. And we think a lot about what can we sense that was not possible to sense before, but how can we also develop sensors for extreme environments to enable societal and ecological applications. And it really depends. So we focus, for example, on sensing for robotics, on sensing for health, and on sensing for climate and oceans. And each of them, we're always thinking about how can we push the boundaries. Probably the most relevant one is in the context of robotics, where we're thinking about how can we build robots to sense things that they cannot see. So over the past probably for the longest time, people have been building robots that enable artificial intelligence, which is intelligence that is like humans. And we try to build the best types of robots that could, and we think that the best robots are the ones that are more similar to humans. But once you're building machines, you can augment machines with sensing capabilities that are not accessible to us as humans. And maybe then you can enable robots to do things that are complementing people rather than necessarily replacing people or becoming more like people. And we are coming, and I've been very impressed and excited about the work that has been happening in the robotics over the past probably 5 to 10 years, especially. And we started thinking even like very recently, okay, people are trying to build robots that can see like humans, but what if you could build robots with superhuman perception? And coming from a background with wireless and RF, we know that wireless signals can go through walls, which is why you can get Wi-Fi from another room. And so we started thinking about maybe we can build robots that could see things that are not visible to the human eye by using wireless signals. And that's what led us down to, okay, today there's a lot of interest in these robots that do, for example, piece picking for a lot of industrial applications, as well as human-robot interaction applications. And we realized that, for example, by tagging objects with batteryless RF sensors, a robot can start seeing an item under a pile, which it could not do with vision. If you give a robot a camera, it cannot see an item under a pile. But once it can see this item, it can maneuver towards it and pick it up and then grasp it and hand it over, for example, to the human, making the whole process much more efficient, because now this robot has superhuman perception rather than human vision.
Great. I think this is going to be interesting now, because I think most of the work in robotics or soft robotics, for example, bio-inspired. And you mentioned something that how we can push the capabilities beyond what we already have. So if you can just about the technique you use, do you think there's a limitation or something I don't know if you have any ideas, crazy ideas that you want to do something also beyond what we already have when it comes to vision as a human? That one example you mentioned, I don't know if you have any other ideas or limitations you think, or features, or do you think about?
So there is this sort of this general technology. I could also talk about the other things that we do, which is also highly relevant to robotics. So for example, one of the areas that we work on is micro implants inside the human body. So over the past probably 10 years now, I've been researching wireless sensing for human health. So how can you use the wireless signals that are around you in order for you to learn about humans? So we talked about seeing through walls, but one way to think about wireless is that we're living in a sea of waves that are invisible to our eyes. But then you could start building smart environments that could like monitor these waves. So every small movement that I do, I'm moving my hands now, I'm talking, I'm breathing, my heart is beating. All of these are associated with small movements. But now, when you try to sense these wireless signals, it's almost as if you're sensing noise, right? So there's so much of this noise, and how do you make sense of this noise? And so the work that we've done in wireless sensing, this can also be applied to robotics, enabling robots to understand humans. I mean, there's this whole field of human-robot interaction, but what if you can also understand, like perceive how people are moving, or even discover their emotions? Maybe there's this person who's stressed working with me. And one of the projects that we had even a few years ago was this, that you could use wireless signals to recognize human emotions, because you're measuring the heartbeats and the breathing. And there's this whole field in computer science called effective computing that allows you to use biosignals to infer emotions. Funny enough, that project, when it came out when it was published, the producers of The Big Bang Theory decided to create an entire episode making fun of how MIT scientists built a device that can recognize human emotions. But over the past few years, we've also been interested in going into the human body and how you can start sensing the human body from the inside. Our technologies for sensing the human body from the outside have already been deployed for monitoring people with Parkinson's, Alzheimer's, even COVID-19. But now we're starting to think about how you can also even monitor the body from the inside and even treat it. And this is what my student who recently just defended, his name is Muhammad Abdulhamid. For the past 4 years, he's been investigating, can we build batteryless micro implants that can sense the human body from the inside? And this is on my side. So he was very excited in building these microchips. What I want is, can we build micro robots inside the body that are also batteryless, that can move inside the human body and monitor it, and maybe if they identify there is something wrong, that is fix it that is potentially fix it. So this is sort of there's always a long-term vision of what we want to do over maybe a decade, 2 decades, 50 years, 100 years from now, and how we can translate these into projects that were towards that we can impact the world in the near field. And then there's this third direction that we work on, which is underwater. I started being very interested in the oceans about maybe 4 years ago. And a lot of this was driven by a desire for us to be able to understand the climate change. Climate change starts in the ocean. The oceans are heating, and that's what impacts us sort of even as humans afterwards. But also life starts in the ocean. Everything starts with water. And so as we started looking into the oceans, we started looking at the literature and realized that more than 80% of the ocean has never been observed or explored. What's crazy is that we know more about the far side of the moon and the surface of Mars than we know about the depth of our oceans, which is where life starts. So my team started thinking about how we can develop sensing technologies for us to understand and decode the ocean. And we realized that one of the biggest challenges in the ocean is that it's actually very difficult to deploy sensors and have them stay there for a very long period of time. And one of the reasons it's hard to deploy sensors is because they need to have energy, and it's difficult to put a battery that lasts for a long period of time. So for example, if I have my phone is plugged in and my phone gets recharged, I can recharge it every day. But if I put a sensor in the ocean and it has a battery, in order for me to recharge it, I need to send a ship, pay between $30,000 and $70,000 a day to replace its battery and come back. And that got us thinking about ways that we could develop sensor technologies for the ocean that don't require any batteries. And over the past few years, we've been developing that. But then we realized recently that that has also applications in underwater navigation, because now you can send a robot and you would not lose a robot because it could use these sensors also to find itself. It's almost like you have an underwater GPS in the ocean for navigation. So a lot of these sort of ideas, whether it's in the robotic space or whether it's in the health or whether it's for ocean sensing, they are at the intersection of sensing, but also perception and decision-making, helping us as humans understand our environment, but also building new tools that allow us to interact with this environment in ways that were not possible before.
Wonderful, yeah. But I'm curious about maybe when it comes to, for example, open-ended environment, and you mentioned the sensor as already don't rely on battery. I don't know what limitation do you think to observation, because for example, one of the projects you used already metamaterials to design that kind of sensor. But if you can tell more about how you managed to do that, what kind of still limitation or questions you still have, or something you still hard to understand how this maybe deploying the system.
Right.
Yeah.
So, yeah. The one thing that I would say is that there are so many limitations to the extent that we are just starting to demonstrate the feasibility. So, for example, you just asked about the underwater project. We just demonstrated that it is possible to build batteryless sensors, okay, for underwater, and we demonstrated that it is possible to use them for underwater localization. So you could use them for localization. But then there's so many questions. How do you build these sensors on the electronic side so that they can last for a very long period of time? How do you build the material so that they can last for a long time? How do you reduce their power consumption even more? How do you integrate them with different sensors so that they can sense their environments? If you think even from a robotics side, how do you build underwater navigation systems that rely on these batteryless sensors as anchors? So GPS, you have satellites, they're in specific positions in space, but these sensors don't have any batteries. So how do you build this control that allows you to navigate? How do you combine these with visual odometry so that you can have, I mean, when you're using vision and then they use acoustic signals, how do you combine these multimodal to enable better navigation? How do you enable robotic grasping in underwater environments? So today this is growing, but if you want to build underwater infrastructures, or even if you want to send something to repair a habitat, to recover underwater habitats for animals, how do you go ahead and build these that can manipulate their environment by combining vision with acoustic sensing? How do you make them at ultra low power? How do you build these systems that can map the underwater environments? We're just talking that 80% of the ocean has never been observed or explored, which means that we need to send robots that can explore them. But how do they use, for example, batteryless GPS in order to navigate, but also combine it with vision and understand where they are? The limitations are, of course, way more than the possibilities. And this is what is exciting about research. It's the fact that you demonstrate that something is possible, but then how do you overcome these problems to deliver on the vision and deliver on the new applications? And frankly, it's the same thing whether it's for the microimplants inside the body or whether it's for the robotic grasping items. All of these have much more limitations than what we've already demonstrated, which is, as scientists, very exciting because there's a long path towards impact, hopefully.
Great. When you look for that sensing design, do you think there's any direction we have to give much more attention or focus? What could be maybe the main component you think we have to give much attention or focus when designing sensors?
I think it really depends on the research style. So as I operate across fields, I really enjoy having sort of doing interdisciplinary work across fields. And I think scientists should operate in what they enjoy. So there's certain types of researchers that really enjoy the application, like thinking about things from an application perspective. So I see this in my students as well. Some of them are much more driven by the application, and the applications are themselves hard, and they also open up what are the problems with the systems themselves. Like they open up interdisciplinary problems. So for example, I have students in my group who are very passionate about underwater ecology. So they want to build these sensors to understand underwater environments. And over there, the challenges are in system integration. System integration is very hard because it requires a large breadth, and also how do you interface a lot of these sensors together. Then there's other types of researchers who really enjoy their disciplines. And so, for example, whether it's in the electronics, whether it's in the robotics, whether it's in the material, and each of these have also subdomains within them. And over there, there's also a lot of open problems. And I think it's the space is so large that the way I see it and the way I also interact with my students is I ask them what they are passionate about. And we try to identify problems based on what they're passionate about from a technique perspective, because there's way more problems than there are solutions out there.
Great. I don't know if you have any kind of thoughts, maybe what kind of features or kind of functionality do you think for sensor you want to have? I don't know if you have any crazy ideas about implementation in your sensor. Do you have any kind of thoughts or idea about that? If you think about it, yeah.
So in the sense of what would I like to sense that is not possible? So the first thing that I would like to do is just even sense things that are possible, but at scale. So for example, I want to really be able to, can we understand the ocean at scale with underwater measurements? So sometimes there you might be able to build, the sensors might exist, but it's very difficult to deploy them and get information from them. Other times it's about how can I reuse an existing sensor to sense something that people did not think was possible. So for example, using wireless to sense the environment when people were using wireless primarily for communication. I think much more from a domain perspective in trying to understand, like I'm very interested from an in-body perspective to be able to understand, for example, can you monitor tumors in better ways? What types of sensors that you do? So I also collaborate with material scientists, researchers who build new, for example, flexible electronics. And we think together about how we integrate these flexible electronics at ultra low power to do long-term monitoring, to be able to do prediction and early intervention rather than having to do it sort of after. Doing things at much earlier stages enables better prognosis and better diagnosis. And we work with medical doctors who sometimes come to us with new types of problems. So for these types of applications, I go to the domain experts who are already working there, and we collaborate together in order for us to be able to identify what is the right type of sensor to build. Personally, I'm excited about what is something that we could do that was not possible before, and what that we could do at the same time to also solve real problems that are facing society. So it's sort of and at the same time, it is hard. So there's like 3 criteria for any research project. A, it's sort of like magic. B is it's technically hard. And C is it can solve a real problem facing society or ecology.
Wonderful. So I'm curious about the learning. When you design the sensor, for example, you have different application for that. But when it comes to learning, the continual learning or being adaptable and have this kind of generic, they can adapt to different scenario and sense something, whatever. How do you think about learning and this continual learning as well for the data you get from the sensors?
Learning is, so we adopt also learning models in our own, in a lot of our systems. Learning is there's some generic types of learning, and then there's domain specific, and my expertise is more on the domain specific learning of the environment. So for example, if you think about wireless signals, you want to use them to learn the environment and understand how the environment is changing, but the environment around them always changes. So you need to be able to adapt to a changing environment, right? So there you need some form of continuous learning, but also with some level of domain adaptation. Sometimes we also work on reinforcement learning, where where the problem is so complex. So for example, especially when it comes to wireless, the problem itself is you do not observe them. So as humans, it's difficult for us to understand them. So we develop learning models that could, based on simulations, that come up with things that are much better crafted than humans could do, just because they have a way of perceiving the environment in a much better way. So when it comes to learning, there's different types of learning that are highly dependent on the domain. And what we do is we try to open up sort of the models and incorporate features that are specific to the sensors themselves, whether it's wireless, for example, with RF, radio frequency signals. There's specific properties that if you incorporate them, the whole learning models becomes much simpler. And so it becomes easier to train these models.
I'm curious to ask you, this is something maybe, I don't know, through your work, the result you got was counterintuitive or surprising, maybe through the way of thinking or the models you expect a certain result, but when you try to go to a real world application, it was counterintuitive or surprising. You didn't expect those results. I don't know if you have any scenario like that happen to you.
It happens almost all the time, and it always happens when something actually works. You know, in science, you don't know why it doesn't work. You don't know why it works, but then suddenly it works. One of my sort of my earliest experiences was when I was building this device that can track people using wireless signals. And the first time that it actually, the way I was working was probably midnight in the lab, and I was trying to track a robot because I was the only person. So I was programming the wire, and the first time it worked, tracking it through the wall, I was definitely surprised that it worked, because sometimes something works on paper, but it's very difficult for it to work in practice. Then the first time we showed that you could use wireless signals to get heartbeats was also, to some extent, a shock. It was very surprising. How do you get sort of heartbeats, which has tiny, tiny changes inside the body? How are you even able to extract them using wireless signals? And then we had to go to the medical literature and try to understand why that is possible to happen. Most recently, probably the fact that we were able to build sensors that can communicate underwater without requiring any batteries was definitely was surprising, in the sense that they were able to work. But then we took them and we started deploying them in the Charles River, which is right across from MIT. And then they stopped working, and we did not know why they were not working. Every time you take something and you put it in a more complex environment, it becomes harder. And so then we started understanding the environment and bringing in our technical expertise from an engineering perspective. And then in order for us to overcome the challenges and get them to work again. If we're not being surprised, it probably means that we're not working on a sufficiently ambitious project.
Yeah, and do you think simulation sometimes, because we speak about simulation to reality, do you think simulation for your work, I don't know, could be save time sometimes to give you insights about this kind of complex environment, or still that a lot of work do you think we have to do for simulating this complex environment?
To be honest, even a small amount of simulation, I mean, with learning models that have a large number of parameters, being able to do simulations always gets you really much better results. the simple fact of being able to do simulations, and of course, developing better simulation models can reduce the amount of training that you need to do in the real world. Simulations are particularly important when you are trying to operate in environments where collecting data is hard, or where you might not even be able to be there to collect data. I mean, think about underwater environments. You're sending something to an area that you've never been before, right? So how do you, so you cannot even train over there. So you need to try to develop a simulation environment that can try to get you sufficient approximation to it with some level of modeling, but you also want to be able to extend it to scenarios that you might not have seen. And in those settings, you have to do it in simulations.
Great. So I'm just asking about the redundancy or resilience, or this kind of scenario failure of sensing. How do you manage this kind of, you still have this kind of sensor still sensing if there's damage happening, or I don't know, scenario like that?
So we've actually seen that a lot when we try taking our technologies, not just from the lab to the world, but also to practical deployments for monitoring people, like for example, with our sensors, monitoring people at home over long periods of time. And you start seeing there's so many of these different failure modes. And there's usually two ways of addressing them. A is, like, for example, one standard approach that we use is multimodal sensing, where you use sensors such that their failure modes are like one type of sensor fails where another one doesn't, or vice versa. The other way that we could do it is sometimes significant engineering effort, just to make sure that you're not giving a false output when it is in a mission critical scenario. So for example, for the first one where you have multimodal sensing, if you think about RF to be able to see things through occlusions, we also use vision. So we combine vision with RF, and then vision can see things at high resolution, but it cannot see through occlusion. So its failure mode or its inefficiency mode is when something is occluded. RF, on the other hand, or wireless signals or radio frequency signals, can see things through occlusions, but they have poor resolution. So this is one of the most beautiful sort of scenarios where you have two sensing modalities that are complementary, and where their failure modes are to some extent mutually exclusive. And so when one fails, the other one works, or where one shines, the other one has limitations.
Great. And I'm curious to ask you about, I don't know what could be the future, do you think, for 5 years coming for designing the sensor? Do you have any kind of, current unavoidable trade-off when you design the sensor? I don't know, through designing this something you can get over this trade-off, and you envision that something maybe can be improved into coming years from real life? Yeah.
I love that question. And my answer to it has always been, I actually don't think that things, when you think about a system perspective, there are very, very few things, and I'm not even sure what they are, which are not possible to overcome. If you were to think about it from a specific discipline perspective, then that might be the case, right? Which is why abstractions between disciplines are great. Sort of discipline boundaries are great, but they're also sometimes very problematic, because when you have abstractions of disciplines, then if you're thinking about a specific type of sensor, like for example, can I use a camera to see through walls? An optical camera, that's probably very hard or near impossible. But if I were to change the question and say, can I see through walls? And then I go to, for example, then that's how we think about RF, for example, as wireless sensing. You could think about the same thing with underwater. Can I achieve batteryless communication underwater? Are you going to be using the existing methods of symmetric communication? The answer is no. If you were to change it to asymmetric communication, then suddenly you start being able to think. So sometimes the question is, what are your assumptions? And if you go ahead and change one of the assumptions, or change the problem itself, then we would be able to overcome a lot of the challenges.
Yeah, that's a good point. Yeah. So I'm curious to ask you, because we close the end about the part of translation from what we do in the lab to industry. I think that's a question, how we can make sure what we do is really beneficial to the people. I think that's what we're trying to do. But what could be the component, or I don't know, how we make sure that's happening, this kind of reproducible sensors as well, and how you see this question? Yeah.
So there's different ways of doing this. And I can tell you what our own style is. Of course, in research, there are two types of research. There's, in general, there's curiosity-driven research, and there's use-driven research, right? And we try to, in my group, we try to really operate at the boundaries of the two. Curiosity-driven research is good in and of itself, because you need to explore. Like sometimes we need to know, we need to get negative results as well. I mean, maybe something is possible, but maybe we realize that it's not the right way to do it. So curiosity-driven research is good in and of itself. We try to choose things at the boundaries where we start with the curiosity, is this possible? And then over time, we start moving it from, oh, is this possible, to how can we deploy it in the real world? And I think this drive is, in and of itself, having this drive of being able to deploy it in the real world is a strong incentive for people to see it. Probably the earliest example for me is we started with, can you see through walls with Wi-Fi? But then we moved it to, how can we use this for real world applications? And we realized healthcare is the right application domain there. And then we started thinking, okay, now we started deploying it out of the lab and into the real world. And a lot of the research that we had done up to that was very helpful. And now it's used to monitor thousands of patients. And for example, now in my group, we're doing this again with some of the work that we've done with RFID perception early on. When I started as a faculty around 5 years ago, we started by thinking, okay, can we do time of flight measurements on batteryless sensors, which was something that people thought was not possible. And then over the years, we've demonstrated that it is possible. We've combined it with automation. And again, now we're taking this out of the lab and into the real world. And we face all new types of problems, but we're building a lot on what we've done before and trying to demonstrate practical use cases in automation, in warehousing, and logistics, and so on. So this, I think if people want, it is possible to follow through from moonshot ideas to the real world, and maintaining both connections with disciplines, with people's own disciplines, because there's a lot of smart people in science, but also there's a lot of smart people in industry who understand what are the real problems on the ground, and being able to bridge these is for us a very happy medium to stay in, so that we also know that we're working on relevant problems.
I'm curious to ask you about the negative result. Do you think that there's a pressure, because we know there's pressure to publish most of the time. I don't know if that's something affecting you when you have this curiosity to a certain project, and it's affecting you or not at all?
So personally, I find myself trying to, for example, push my students to think about what is the long-term impact rather than what is the minimum publishable unit. It's also, writing really good papers is hard. If you want to write papers that are very accessible to a broad audience that can have a lot of impact, is hard. Negative results can be folded into positive results as well, in the sense that you could say, look, I tried all of these things, they did not work. And I tried these things and they actually worked. So in my group, we try to not publish a lot of papers, actually intentionally, and we try to build systems and deploy them into the real world. I actually think there is a misconception that a larger number of papers is better, like that people will measure by the number of papers. You probably don't remember Einstein by his number of papers, right? You remember by for example, the like E equals MC squared, or the duality between light and matter. And at the end of the day, people in the long run are remembered by core contributions much more than it's actually not a great thing to be probably only in academia people would appreciate, oh, this person has this number of papers. It is much better to say that this person demonstrated that this thing is possible, right? So people to be known for specific things, or that they are pushing things. And so this is where my role as an advisor is to help my students not be stuck in rabbit holes, but also to guide them towards thinking about big problems and how we can also divide them into publishable things, because research itself, I mean, the other type of learning is research itself is a learning process, the end of which we teach the world. So we want to make sure that we are learning, not just producing output. And part of it is we have the luxury of doing that because we are in systems. So we have to build things to show that they work. And then we have to deploy them to show that they are also useful.
Thanks so much for that. So it goes with a few questions. Do you think ego is important for you as a researcher? Because sometimes you have this new idea of something and you think in academia sometimes it could be sometimes an ego-driven system. So you have ego when it comes to discussing your ideas, or
there's I think there's two different types there's different ways of talking about it, right? Ego in and of itself is not good. So you need some level of self-confidence. That is important, but you also want to be, I think ignorance of that something is not going to work is more valuable than ego that it will work, in the sense that you want to be in an area where actually a little bit more ignorant and be able to ask questions that show how ignorant you are. But you also want I'd say a personal drive, a certain level of confidence that you will be able to follow through, because research, you're always sort of battling against the wall. And I think this is actually quite common at MIT, in the sense that I remember being, when I came as a grad student, sitting with my advisor, and I was like, and she would ask all of these questions that I was like, isn't she like concerned about sounding like not smart or dumb for asking these questions? And I realized that, in fact, if you were to ask her about her area, her primary area of research, then she is an expert in that area. She would probably like argue with the person up until the last bit. But if it's a new area, you want to be able to you want to embrace your ignorance so that you can learn. And I've adopted that as well. So for example, if I'm in a new area, I don't have a problem being thought of as ignorant, because I'm probably ignorant in that area. And that is how you develop your expertise, by learning. So not shying away from it, but also having the confidence in our own earlier contributions. That, I mean, if someone is going to come and ask me about things that I've published on, then I might as well really know how to defend them to the last bit. And this is also part of being what I started by saying, is that I enjoy thinking about moonshot ideas, but also investigating them with scientific rigor, so that we really understand what we're talking about.
Wonderful. So I don't know what could be the most important quality you have gained so far, being in academia, or maybe the research. What could be the most important quality?
I think the hardest and most important quality is probably, how do you balance between questioning yourself and also being able to drive things forward, in the sense that when people are working on research, is always working on some level of risky ideas. So, and you're going to get most of the time more negative feedback than positive feedback. So at what stage does this negative feedback, how do you learn how to internalize it and say, look, I need to pivot, like push or pivot, right? Proceed or pivot. Developing the judgment of knowing to proceed or pivot is the hardest quality. And I would say this is not just in research, it's also in advising, like how I advise my students and how I mentor my students. Do I keep doing the same thing, or do I pivot to a different approach? Or even in life at large, like, do you keep doing the same thing or you pivot? The best quality is a refined judgment of knowing of proceed or pivot. And this is very hard in any field and in any aspect of one's life. And it's particularly important in research, because you need to know every day, should I keep moving forward or should I pivot? Based on all the negative feedback that I'm getting as well, which is much more than the positive feedback that we get in research.
Absolutely. This is very profound. Yeah. Two questions. Like the first one, what is your favorite book? I don't know, maybe in the field or outside the field. What is the favorite book?
In my field or outside the field?
Yeah, as you like. Maybe a book stick to your mind and you would like to share with the audience.
So frankly, I invest much more time in reading papers than reading books.
Okay.
I review more than 100 papers per year. When I read books, I actually read more books on like coaching and management, because as a faculty, I mean, I have to. I'm also to some extent a manager, and that was the area that I had least training in. So probably my best books, the books that I usually recommend are more on how do you develop your management skills, because these are things that I wish people learn more about, because especially when you're managing or coaching other people's, I think an advisor is primarily a mentor and a coach. And you're influencing people in ways beyond what you believe. So it will probably be in that rather than a technical book.
Yeah, great. Yeah. And I'm curious to ask you what is your aspiration, maybe, and what you're doing. What are your aspirations?
Well, there's different levels of aspiration, but
Yeah.
probably leaving a positive impact on humanity for a very long time. That would be the ultimate aspiration, and trying to maximize that level of positive impact.
And lastly, what would be the best advice was given to you and was life changing advice to stick to your mind?
The best advice that was given to me. Oh my goodness. I've benefited from an enormous amount of advice. I'm not sure if there is just one specific one. Technically, the advice was basically keep questioning any result, just question it to the core before others question it for you. Being ambitious, being hardworking, there's the standard things, but also I would say a more general piece of advice is probably be empathetic with anyone that you're working with. Is probably more important than anything else, because we are researchers, but we are primarily humans.
Thanks so much, Fadel. It was such an honor and pleasure to listen to you. Thank you, and thank you for your time.
It is my pleasure.